Welcome back to the Deep Dive, where we take the most complex research and turn it into the knowledge you need right now. Today, we are peering inside the very core of cancer diagnostics, but we're doing it in a way that feels a little bit like magic. Imagine taking a plain, centuries-old diagnostic slide, the standard biopsy photo every pathologist already has, and finding deep, high-resolution molecular secrets buried inside it.
That really is the mission today. We are tackling what has long been, the greatest hurdle in spatial biology.
Spatial biology, let's define that right up front.
It's the study of knowing exactly where specific proteins are located within a tumor, how those cells talk to each other. And it is fundamentally transformative for understanding and treating disease. The problem is the tools are they're far too expensive.
Too expensive, too complex.
And too slow for routine clinical use, especially in, your average community hospital.
So we have this huge bottleneck. We know the location data, the spatial context matters profoundly, but the technology to map it is stuck in the research lab.
Precisely. And our source today, a major study published in Nature Medicine, introduces an AI tool designed to break that bottleneck wide open. It's called HEX. That's short for H&E to protein expression.
H&E to protein expression, okay.
And this model creates what they call virtual spatial proteomics. So our deep dive is all about unpacking how HEX provides this molecular shortcut. And, more importantly, why its ability to predict cancer prognosis and immunotherapy response across thousands of patients is so revolutionary.
And the scope of this work is massive, right? I mean, this isn't just a small pilot study.
Oh, far from it. The training data itself is immense. We're talking 819,000 histopathology image tiles from 382 tumor samples. And while the focus was initially on non-small cell lung cancer, or NSCLC, the study meticulously proves its generalizability.
Across other cancer types.
Yeah, across dozens of other tissue types, which makes it immediately scalable for the clinic.
Okay, let's unpack this core mechanism first. So when a pathologist first looks at a tumor, the starting point is always the H&E slide. H&E is hematoxylin and eosin. What are we actually looking at when we see that slide?
That's right. H&E staining has been the clinical gold standard for diagnosis for ages. The hematoxylin stains the cell nuclei, a blue or purple color.
Okay.
And the eosin stains pretty much everything else, the cytoplasm, the extracellular matrix pink. It gives you the general tissue architecture. It's the basic map of the cell structure and how organized or disorganized the tumor is.
So that's our basic map. Now, the high-tech destination we want to get to, the information that's currently too expensive, is spatial proteomics. What does that actually give us that H&E can't?
Spatial proteomics, and specifically the technology they use for training called CODEX.
CODEX.
Stands for co-detection by indexing. Think of it as a molecular GPS for the tumor. Instead of just seeing blue nuclei and pink cytoplasm, CODEX identifies and quantifies the expression of over 50 different protein biomarkers simultaneously.
50? Wow.
And it does it at single-cell resolution across the entire tissue section.
So instead of just seeing a blob of cells, you see which ones are T cells, which are macrophages, which are proliferating aggressively, and exactly where they are relative to each other.
Exactly. It's a high-dimensional mapping system. It shows you identity and function in a spatial context. But the clinical challenge remains. CODEX requires these specialized $500,000 instruments, highly trained personnel. The whole thing is just not scalable.
Right. So we have a cheap, ubiquitous map in H&E and a transformative but incredibly expensive molecular map in CODEX. Enter the AI. HEX. How does it jump this immense gap?
The AI is essentially learning a sophisticated high-speed translation key. HEX is a generative AI model. It's built on what's called a pathology foundation model, like the MUSK backbone, which has been pre-trained on millions of pathology images already.
So it's already an expert in looking at tissue.
A huge expert, and it takes the cheap H&E image as its input, and from that it predicts the expression of 40 specific protein biomarkers. And it does this all at once, simultaneously.
That's critical. It's not just guessing one protein, it's generating an entire high-dimensional protein profile for that specific spot on the slide.
Precisely. And the training process was the real key here. They used 755,000 small image patches, each about 50 micrometers square. And these were all generated from the exact same tissue sections that were stained with both H&E and the 40-plex CODEX.
So the AI gets to see both pictures for the same spot.
It gets to see the question and the answer sheet nearly 1 million times. It looks at the incredibly nuanced patterns visible only in H&E, like the subtle texture of nucleus or the cell density, and it mathematically maps those visual features to the specific cocktail of 40 proteins that it knows are present in that exact location.
This brings us to a perfect analogy. If the standard H&E slide is a simple, cheap road map of a city showing only the main streets,
Right.
then traditional experimental codex is an incredibly expensive real-time satellite scan showing every single car, person, and what they're doing, down to the individual building.
And HEX, the AI, uses that cheap road map to virtually generate the satellite scan. It delivers what they call virtual codecs, all that incredibly detailed, expensive, high-plex molecular information from the low-cost H&E slide you already have in the clinic.
That is the definition of disruption.
It really is.
Let's hit the recap right there, because this mechanism is the foundation of the whole study.
Absolutely. The core idea is pretty simple, when you break it down.
First, the problem.
Spatial proteomics, or codex, is just too slow and expensive for routine use.
The solution.
HEX. It transforms the cheap H&E slide into a high-resolution molecular protein map, a virtual codex.
And the training power.
Nearly 1 million co-registered images let the AI learn the subtle visual clues of what molecules are where.
Which means the impact is.
It removes the major clinical and financial bottleneck in spatial biology. It democratizes it.
Okay, that covers the mechanics, but this is medicine, not science fiction. You can't base treatment on what might be a highly correlated hallucination. We need rigorous technical validation. Is this virtual information accurate enough to trust a patient's life with?
That's the exact question the researchers had to answer, and this is where the study really shines. They used robust metrics to gauge accuracy, like the Pearson's correlation coefficient, or R.
Right, the R value.
This basically measures how closely the predicted protein map matches the actual physically measured codex map. In their cross-validation, HEX achieved an average Pearson's R of 0.790.
0.790. For our listeners, give us a sense of scale for that number. Is that good?
It's incredibly good. Think of it this way. If a perfect flawless match is 1.0, HEX is hitting nearly 80% accuracy in predicting where those 40 markers are. It's generating a virtual molecular map that is, for all intents and purposes, indistinguishable from the real one.
And how did it stack up against other AI models?
They benchmarked it against existing state-of-the-art generative models, like CGANs, conditional generative adversarial networks, and HEX blew them away. It had a massive 46% increase in that Pearson's R value and an 80% reduction in prediction error compared to the next best model.
So not a small improvement, a massive leap.
It's a paradigm shift in reliability.
Okay, accuracy is proven, but medical data is notoriously messy. How do we know this isn't just some incredibly specific algorithm that only works on, say, lung cancer tumors prepared in one lab on one specific scanner? Is it generalizable?
That was the next major hurdle they cleared, and it's arguably the most impressive technical achievement of the whole paper. They validated HEX on 2 large independent tissue microarray datasets. But crucially, they really pushed the generalizability envelope. They tested the model in a huge pan-cancer dataset. We're talking 206 tumor cores spanning 34 distinct tissue types.
34. So things like liver, breast, pancreas.
Liver, breast, pancreas, kidney, you name it. And these samples would have been prepared using totally different staining protocols, digitized on completely different scanner platforms.
Different ingredients in a different oven, so to speak.
Exactly. It's like teaching a child to recognize a cat from a digital photo, and then showing them oil painting of a cat, and they instantly know what it is. The fundamental concept holds, even when the medium changes dramatically. And the performance, even without any fine-tuning for these new tissues or scanners, remained incredibly strong. It still achieved a mean Pearson's R of 0.658.
Which proves the model is universally applicable. It's scalable.
It really is.
So once this virtual codex is generated, you have this massive data file of 40 proteins mapped to every cell. How do you actually use it to make predictions? You need a bridge, right, to connect this new molecular data back to the physical structure on the slide. Is that where the MICA framework comes in?
That's where the magic of fusion happens. MICA stands for multimodal integration via co-attention. And it is the critical clinical step. It takes the features from the original H&E image, which capture the morphology, the structure, and it fuses them with the features from the AI-derived virtual codex, which capture the molecular patterns.
Why is that fusion step so vital? Why not just use the virtual protein data on its own?
Because H&E tells you what the cells look like, and virtual codex tells you what the cells are. You need both. MICA uses this co-attention mechanism to explicitly model the interactions between the two. It makes sure the final prediction uses the tissue structure and its virtual molecular landscape at the same time.
It gives you the most complete picture possible.
The most comprehensive picture, exactly.
Let's pause for a second, recap right here, this time focusing on the readiness of this tool.
Sounds good. 3 key things to remember about the validation.
Okay, number 1.
Accuracy established. HEX is highly accurate, that R value of about 0.790, and it's far superior to other AI methods.
Number 2.
Robustness proven. It works consistently across 34 different cancer types, and despite variations in lab protocols and scanners.
And finally, what makes it usable?
Clinically ready. The MICA framework successfully combines the visual data from H&E and the virtual protein data, creating a single, powerful, predictive tool.
Now we shift to the clinical so what. How does this combination of basic histology and advanced virtual proteomics actually translate into better patient care? Let's start with prognosis in early-stage non-small cell lung cancer, where an early, accurate diagnosis is so vital.
Right. They evaluated the prognostic ability across 5 independent cohorts of early-stage NSCLC. In total, 2,150 patients. And the results were dramatic, mostly because they directly compared the MICA predictions to what doctors use today.
Give me the headline statistic on that prognosis improvement.
The MICA-enabled multimodal integration improved prognostic accuracy by a substantial 22%.
22%.
22% compared with relying on conventional biomarkers alone, like tumor stage and grade. For stage-IS NSCLC patients, who often have excellent prognosis on paper, the model consistently and successfully sorted them into high and low risk groups for recurrence.
So MICA is finding the high-risk patients who might otherwise look low risk based on standard staging. The stage says they're fine, but the virtual molecules are telling a different story.
A much more dangerous story.
But here's where it gets really interesting for me. What was the biological aha moment? What molecular landscape was the AI actually using to make these better predictions?
The interpretability is key, you're right. They use these advanced methods to basically peek under the hood of the AI and see what it was paying attention to.
So let's start with the good news. What characterized a patient with a good prognosis, the low-risk group?
The low-risk tiles, the ones that predicted a good outcome, were consistently enriched for key immune markers, CD20, CD3E, CD8, and granzyme B. Which, in lay terms, these are the signature molecules of a strong army of T cells and B cells, actively hunting and killing the tumor. Specifically, the AI flagged a high prevalence of what are called CD3E plus pan-CK plus tiles.
Okay, break that down.
Pan-CK is a marker for the tumor epithelial cells themselves. CD3E is a marker for T cells. So that signature means T cells are actively infiltrating the tumor. They're inside the enemy camp. There's a very robust, healthy sign of an anti-tumor immune response.
Wait a minute. So the AI, looking only at the H&E slide, was able to infer the presence of active infiltrating T cells, something a pathologist could never reliably guess just from the shape and color of the cells alone.
That's right. And then on the flip side, what about the bad prognosis, the high-risk features?
Yeah, what did that landscape look like?
These tiles showed significantly increased expression of a proliferation marker called Chi67. And the most defining spatial patterns were high fractions of Chi67 plus pan-CK plus tiles.
Meaning hyperproliferative tumors.
Exactly. And even more concerning, high fractions of CD44 plus EBCAM plus tiles.
Which means?
That reflects the presence of cancer stem cell niches.
Wow. So the AI inferred the presence of highly aggressive cancer stem cell niches, which, again, a standard pathologist would never have seen on that basic slide. The shape of the cells on the H&E contained these hidden clues to their stemness and their proliferative potential.
It did. It didn't just improve the prediction. It offered an interpretable roadmap for why one patient did better than another, down to the specific cell interactions driving recurrence.
Let's move to the final and perhaps most critical application, predicting response to immunotherapy. Immune checkpoint inhibitors, ICIs, are revolutionary, but they only work for a subset of patients. Predicting who will benefit is the current holy grail of oncology.
It is the ultimate clinical challenge. For this, they tested HEX and MICA on 148 patients with advanced NSCLC, all treated with anti-PD-1 or anti-PD-L1 ICIs.
And how well did this virtual approach predict who would respond?
MICA achieved an area under the curve, or AUC, of 0.82 for objective response prediction.
Okay, 0.82. Contextualize that for us.
It's a dramatic performance gain. It improved prediction accuracy by 24% to 39% over the established standard clinical biomarkers. I mean, if you compare MICA to the 2 most common biomarkers we use today, PD-L1 expression had an AUC of 0.66.
So a coin flip is 0.5, 0.66 is not great.
Not great. And tumor mutation burden, or TMB, had an AUC of just 0.59. MICA at 0.82 just blew those established benchmarks out of the water.
The fact that an AI looking at a basic H&E slide outperformed the current gold standards for immunotherapy prediction it's stunning. Again, what was the biological secret here? Was it a single marker, or was it these spatial co-localization signatures, these SESs?
The predictive power came almost entirely from those spatial interactions. Single markers on their own often failed. But the spatial co-localization, the neighborhood, was the key.
So let's focus on the responders first. What did a tumor microenvironment, a TME, look like for someone who had a good response?
Responders were characterized by this coordinated spatial co-localization of multiple T-cell subpopulations. You're seeing a thriving immune system it's ready to be reactivated. Specifically, they saw strong clustering of granzyme B plus CD8 plus, those are the cytotoxic T cells that actually kill cancer, alongside TCF1 plus CD4 plus cells, which are the helper T cells.
So the killers and their support crew.
Exactly. And some PD1 plus CD8 plus cells, which are the exhaustant T cells. But the fact that they're all in the same zip code suggests they can be successfully reinvigorated by the ICI therapy.
It sounds like the T cells were already there, doing reconnaissance, but just needed the ICI therapy to take the brakes off. And the non-responders, what was that high-risk TME like?
Their tumors were defined by immunosuppressive cells that actively shut down the immune response. We're talking about the bad actors. Pro-tumor neutrophils, which are CD66B plus MMP9 plus LMA, and M2-like macrophages, which are CD163 plus MMP9 plus DANE.
And the key is that they're clustered together.
The key is their spatial proximity. They are aggregating. They're forming these physical immune barriers, creating an immunosuppressive and fibrotic environment that physically prevents the killer T cells from even reaching the tumor.
This has immediate clinical implications. The study noted, for example, that even among patients with PD-L1 high tumors who we expect to respond well, 40% did not have a durable response. MICA helped identify those patients, suggesting they might need combination therapy right away.
And conversely, it gets even more interesting. MICA identified 29% of patients with EGFR mutations, who were generally considered resistant to ICIs, who did actually get a durable clinical benefit. HEX provided the clarity to refine these crucial treatment decisions based on the actual spatial biology, not just on single gene mutations.
This research is it's truly groundbreaking. The clinical utility is undeniable. HEX offers a low-cost, scalable, and biologically interpretable path to study spatial biology that performs, it seems, just as well as high-cost methods like real codex in these kinds of studies.
The line between a standard diagnostic image and a deep molecular profile is rapidly blurring. This technology means the small rural clinic can now access the same high-resolution spatial data that was previously reserved for the world's most elite research hospitals, all from a $20 slide.
We've established that single markers like PD-L1 failed pretty dramatically, but the zip code of cell interactions succeeded. It forces us to ask, if spatial location is the critical determinant of cancer response, is every standard pathology report that relies only on the quantity of cells, rather than their arrangement, missing the most important piece of the puzzle?
And if H&E can be virtualized into 40-plex protein data, what other expensive molecular tests currently reserved only for research do you think AI could virtualize next? All using nothing more than the clinical imaging data we already have. That's something to ponder until our next deep dive.